Welcome back. Today I want to feature some of the ways that we come up with functions in the first place. I claim there's really generally two techniques that we use for making functions. The first one is to measure something, and the second technique is to calculate from the measurement. And I'll be focusing on the second class, but to get there, I want to think about first of all what it means to even measure. Suppose that I look at the shapes behind me. If I want to measure things about them, there's a number of things I could do. For example, I could see how long the side of something is. When I do that, I typically compare it to some other known length. For example, the length of my piece of chalk. I see that that's 3 chalk lengths long. I would now say that it's a unit of 3. The unit here is the chalk length. Now, over the course of humanity, we've set up a lot of standardized systems, a meter, a foot, a yard, whatever measurement system you prefer. But that's not the point. The point is that we're trying to put a number to whatever it is we're measuring. Now, another measurement we'd like to do is to figure out how much paint it would take to cover that side of a wall. We could call that the surface area. We've all learned that there are ways that we can get by without doing that kind of measurements. We can often use measurements on the sides of these shapes and then infer through a calculation the measurement we don't have. And this is where science really gets going, because we often have access through easier means to some measurements that only reveal the measurements we're after through some calculation. So if we start with measurements, then we have to create an apparatus that designs how we'll actually come up with something. It could be a scale that measures weight, a voltmeter that measures potential, any number of measurements. Once we have those, the rest of it is left to computations and calculus. Whenever you have a system for calculation, we call it a calculus. And so today I'm going to investigate how we can describe new functions using the calculus of measurements that we see in everyday life, such as measurements of lengths, areas, volumes, and whatever other names. I'll call them all uniformly measurement. The idea is the same, just with different vocabulary. When I measure, I compare one length to another length. For example, I could use the length of this piece of chalk. That box is about 3 chalk lengths wide. Good handwriting skills. And it's 2 chalk lengths tall. It's pretty remarkable that I freehand drew a perfect 3x2 rectangle. Of course, you weren't around when I measured it, so who knows what really happened. What I see about these outside measurements is that they help me predict what's happening on the inside. For example, suppose that I wanted to talk about area, the amount of paint it would take to paint this rectangle. I could hold up a swatch of paint for which I already know exactly 1 drop of paint covers this much area. Then, I'd hold up my little box, and I'd cover each of these, and I'd discover that it took 6 of my paint swatches to cover the entire square. I now know it takes 6 drops of paint to cover this square. That's the idea of the difference between length and area. Length was a measurement on these sides, and area was a measurement that covered 2 dimensions. However, they're intimately linked. And that's because of what's the law of integration. The law of integration is a situation in which measurements of the whole can be understood as the sum of their parts. This is not going to be true of all data sets. There are many scenarios where things are emergent features. Once enough parts get together, they become something bigger than what you would have expected from the smaller parts. You put gears together and suddenly they can tell time, like on a watch. That feature is an emergent feature. But for a simplified view of many structures, they will have this integration property, that the whole truly is the sum of its parts. Once we think of sum, we think of an algebraic formula to do this. In this picture, we actually see this rule applied in 2 different ways. For example, the length along the bottom is the sum of the 3 individual smaller lengths, the 3 parts. Furthermore, the total area is the sum of the 6 squares that I have in there, the 6 parts. There are many scenarios in life that have this property, and when they do, they're open often to a situation where we can calculate new data from old data. This would be something we could see in the field. We might approach a situation where we can't do all the measurements or it'd be too expensive, but we can measure some parts and use calculations to predict the rest. If we have the law that the whole is the sum of its parts, then we can reduce this to smaller pieces. Now, because this is leading to a system of calculations, it is a calculus. We can take this as a definition of the integral calculus. We think of it as integrating being all the little parts put together into one unit. The whole is the sum of its parts. Therefore, if I know the measurements of all these individual squares, I'm able to get the measurement of the whole. This same idea can be associated with more obtuse shapes, such as a semicircle. What I can do is I can try to subdivide this into shapes that are approximately shapes I already know something about. At some scale, this starts to look like 4 triangles, all of the same size. And if I know the area of a triangle, then I can say that an estimate for the area of the shape behind me is the area of the triangle multiplied by 4. I'm simply using the law, the assumption of integral calculus, that the whole is the sum of its parts. But of course, if we keep on this spectrum, we can find harder and harder shapes. If we want to take the surface area of my soda can, I would have to find a lot of parameters, because there's a lot of contours in here, and the surface area might actually be influenced by all those different turns. So we'd like to build a tool that's robust enough, but all we know at the beginning is that the whole should be the sum of its parts. We want to exploit that rule, but make it something that we can do computationally, something we can hand over to the machines. For that, we often use algebra. Algebra is the tool that lets us take ideas that we have in principle and write them down as something we can do computationally. So what algebra pairs well with what we're doing? Length times width. Rather than calling them length and width, let's assign them axes values. The traditional x-axis is the horizontal and the y-axis goes up and down. The range of change over the x-axis I'll denote by delta x. If this part starts at x1 and that part ends at x2, then it'll be x2 minus x1. Likewise, the change in y will be denoted by delta y. Once we have that, we have these measurements on the side, these lengths, which are enough to calculate the measurement on the inside, the area. And it's no coincidence that we chose multiplication as the model for the inside area. It's because we want to honor this law of integration, that the whole is the sum of its parts. Let's take, for example, that the bottom length, which is delta x, has now been subdivided into delta x1, delta x2, and delta x3, three smaller lengths. These might be of different sizes. They don't have to all be equal. What I would now do is in my formula, my multiplication, I'll replace delta x. Now, because this is multiplication, it distributes over addition. We now see that if these are each capturing area, then what we've just done is captured the area as a sum of three smaller areas. Which smaller areas? This entire size here, that one here, and that one there, because they all have length delta y. If we also want to factor in the change in y, we can do that as well. Now we distribute the delta x's across the delta y. We now see that the area boxes have the same decomposition as our algebra has. We've simply used the distributive law to replace what we were drawing in pictures. The ability to connect how we distribute the boxes in the picture with how we distribute the arithmetic is the connection we need to turn the integral calculus into a computational tool. You might have a philosophical question on your mind. Why is it that dividing an area like this happens to line up so nicely with the distributive law of multiplication? There's a whole lot that could be said on this, and the real ways to dig into these sorts of concepts is by reading a book on the philosophy of mathematics. I recommend Joel David Hampkin's book, which has loads of examples of real-life situations where the mathematics has an uncanny relationship to what we actually do. Sometimes it's a surprise, but often upon thinking about it, we discover we designed the math to match the world around us. So perhaps it's not a surprise after all. Whatever way you think about the connection, it's now one we want to exploit. Suppose I want to work out the area of that triangle. Perhaps the easiest solution is simply to observe that I could double the triangle and create the rectangle. Therefore, if I assume that this law of integration holds, that the sum of the parts is the same as the whole, then the area of the whole is the same as twice the area of the triangle. Therefore, the area of the triangle is half the area of the rectangle. But conveniently, because this is still based on multiplication, it has some of the distributive properties that we were expecting before. That is, if I wanted to subdivide this into smaller triangles, I might be able to add a mixture of triangles and rectangles. For example, if I want the area of this shape, I can think of this in one of two ways. I could extend this out to a larger triangle and then subtract off the area of that triangle, or I could subdivide it as a rectangle and then add it to the area of the other triangle. Now, this was a case where we could see how to fit our triangle inside of a rectangle and therefore borrow the argument about what the area of a rectangle is. But what if we wanted to skip that observation, or we just simply didn't know how to turn the triangle into a rectangle? What would we do then? Starting at this triangle, I could try to hunt for rectangles living inside of this triangle. That rectangle occupies some portion of the total area of that triangle. If I write that down, it's an underestimate. I could add in more, though, to improve my estimate. With the addition of these two smaller rectangles, I still have the area formulas for those rectangles, but I'm getting a closer approximation to the area of this triangle. I'm filling in more of the triangle. And so I could repeat this process. In time, if I keep adding more and more rectangles, it'll become almost impossible to tell the difference between the area of those rectangles and the area of the triangle. We could say that the area is well approximated by adding up those rectangles. In fact, we could even run a contest. You could issue to me how precisely you want to measure the area of your triangle, how many decimal places of precision. Then I would have to choose how many boxes to add until whatever I measure is within that many decimal places. You can see that I could always achieve this because I could always just keep adding squares into that until I fill up as much of the area as your decimal places approximate. It might take me a longer time than your method, but it would eventually get you the same approximation. This is what's known as the integral method. It's a method of getting an approximation for an area by using only rectangles and assembling them in many ways until you fill up more and more of the box. The goal is always to get within a threshold, a margin of error. Without the margin of error, it's not precise what we mean. It would be an infinite process to put in all the boxes. So let's write down what this would mean as a formula. We can see at the beginning that we're going to have a bunch of individual boxes, so we need to name those. And we also need to sum them all together. We can think of the boxes as simply numbering them. The first box, the second box, the third box. We call them all area A sub A. Then, if we write a program to do this, it simply needs to add up those areas. Assuming there are n of them to sum up, it could look something like this. Well, now let's try to make this more systematic. It was a bit ad hoc how I started putting in rectangles. I just chose the first one and then kept adding wherever I was missing. But I could actually be more systematic and make sure that the program wouldn't actually have to guess where to add the next box in. To make this into a program, let's systematize how I create the rectangles. For example, perhaps I simply always add to the right and I do them in equal steps. What I've done here is I've evenly divided my bottom base. And at each base step, I put a rectangle, the biggest rectangle that would fit inside my triangle. Here, because it starts at the corner, I can't go up at all. The biggest rectangle I could have has area 0. Once I've stepped to this unit, that unit can go all the way up to this line and stop there. Then the next one and the next one. What this then does is give me 4 boxes that approximate from below the total area of this triangle. And because this is systematic, I could later improve my estimate by adding more boxes, and I would only have to change one parameter, the number of boxes that I use. I do that by subdividing differently. Having divided them into smaller shapes on the bottom, I now fit more boxes in, and I get a better approximation. Because of this technique, I can go ahead and refine the way that I write my sum. I can now see that I'm going to have A1, A2, A3, all the way up to the total number. So really all I need you to tell me is where to start and where to stop. That'll change my sum notation in a small way. I put the starting point below my S and the ending point above my S. Furthermore, since everything here is a rectangle of even depth, I can simply focus on how high it is. So here we have the general formula. Because each box has a width, let's call it delta xi, we then multiply that width by the total height, yi. That then gives me a sum from the starting point A to the ending point B. This has become so routine that we don't even have to write the word sum anymore. We simply just write the letter S. But we still have one piece missing. The conditions of our game is that if anyone challenges to improve the accuracy of our estimate, we can always do that, which means we're not fixed with one specific list of xi's. Rather, we are saying that we have a comfortable formula that if you ever want us to improve our accuracy, we'll add in more subdivisions that make us ever more accurate. Our notation for that needs to change. Since delta xi seems to care about the specific counting, we'll simply get rid of the I and talk about a parameter called dx, which tells us subdivide as many times as needed for the accuracy you want. So there's the final form. This has become so synonymous with calculus that you've probably seen in the background of movies. Whenever some scientist is talking about some incredible idea, they often have one of these symbols in the background. It's known as the integral. It's given that name because it satisfies the properties we want out of an integral calculus, a calculus that measures things as the whole being the sum of its parts. The sum is this first big part, and we're going from A to B. And the parts are these little y-x's times their thickness, dx's. Keep in mind that there's a lot of style points given to the writing of integrals today. It is very common for this s to get elongated as a long stretching out symbol, something like this. Because of the name integral and because of the way we stretch out the letter s, it is often confused with the letter I. The boundaries from A to B are there to remind us where we start and stop. The heights are given by the yx, and the dx's are a reminder that we need to be given a precision to aim for, and we'll compute it to within that accuracy. We may do much better than that, in fact. Now, this is a lot of heavy lifting to do something as simple as a triangle. And that's because a triangle has a very simple way to be turned into a rectangle. We just double it. But where this becomes more powerful is when we change the shape to something like a circle or a semicircle. If we apply this to the bounding area of a semicircle, we can still subdivide this into equal units. And then we can put the boxes underneath. If we add up all those areas, we get a good approximation of the semicircle area. There are some shortcuts that are really the essential part of this technique. Let's think back to what it is that started this whole thing off. We started off with the attachment of multiplication to the area of a rectangle. Then we went hunting for places to put rectangles. But if we dwell on the property of being a multiplication, we realize that multiplication comes with a partner, that is, division. Division is one of the ways that we can solve for a missing piece. If we expect it to be a product, we divide by whatever it's a product by, and we'll solve for the missing term. So whether we want more precise formulas or faster formulas, it makes sense to consider if we're fully using the integral assumption. That is the whole the sum of its parts? In this case, we're not quite reaching the whole. We're always leaving something out. That leaves the approximate nature of this integral. So it might be worth revisiting the original question. Is there a way to measure the whole as the sum of its parts using different parts? That is, maybe we don't have to start with rectangles. Until next time. That's how you take care of your chalkboard.